modulation and related problems in this session. Okay, the first thing we have already seen about the intro of pulse modulation and types of pulse modulation at all. So we are going to see in detail the pulse code modulation. Uh, Pulse code modulation, simply it is said to be a PCM. So what is the basic concept of PCM in the sense? The analog pulses simply converted into coded pulses. This is the one-line definition of PCM. The analog pulse is the analog signal simply converted into the coded pulses. Okay, then it is here one of the digital pulse modulation technique. This is the digital pulse modulation technique. Then in this pulse code modulation, we have three important blocks. That is the transmitter, transmission path, and the receiver. So the function of transmitter is it's simply used to transmit our information. It's simply used to transmit our information, and that information is posted or conveyed to the transmission path. The function of the transmission path is it's simply carry the information received, simply carry the simply convey the information which it is received by the transmitter, which it is received by the transmitter. Then a receiver is used to convey the information to the information sink. Next, this is the simplified structure of PCM. So here we'll have three important structure, three important blocks we can say. That is transmitter. Transmitter includes low pass filter, sampler, quantizer, encoder. Then transmission path includes regenerative repeater. Then receiver includes regenerator, decoder, low pass filter, receiving end. So what is the function of the transmitter is it will do some pre-processing steps and convey that information to the regenerative repeater, or simply we can say a transmission path. Okay, so what are the pre-processing steps involved are done by the transmitter in the sense the first thing we are transmitting our analog input signal to a we are passing our analog input signal to a low pass filter. Well, the function of the low pass filter is simply filter our message signal alone. It simply filter the input signal to getting our message signal. It simply eliminate the high frequency component. Why? Because high frequency components are simply said to be a noise. Then it will go to a sampler. That is our message signal alone will pass to the sampler block or sampler circuit. So what will happen in the sampler in the sense the given analog signal is get sampled by using the sampler. In this sampler we'll have two types: natural sampling and flat top sampling. Maximum or most probably we are using a natural sampler or a natural sampling method to get the samples of our analog signal. Then the sampled signal will pass through a quantizer. The function of the quantizer is the input of the quantizer, that is the input signal is discretized in time domain. That is the function of the quantizer. So at the end of at the output of the quantizer we are getting the discretized signal in both domain, time and amplitude. So time and amplitude, in both time and amplitude, where the given input signal is discretized. Then that discretized signal will pass through a encoder. So with respect to our input signal, we are getting the pulses respective we are getting the pulses with respect to our input signal. That is, the input signal is coded with the help of encoder. That is, the sample values we are getting the respective digital input for our samples. Okay, for our samples. So we can say we are getting the um, uh, digital codes of our sampled signal. Okay, then it will transmit to the transmission path. Here we'll have the regenerative repeater. It simply reconstruct our received pulses in the exact amplitude and time domain, time information. With the exact amplitude and time information, it simply reconstruct our received signal. By the traveling or while along the traveling, the signal got distorted or corrupted by the noise. That noise can be eliminated, and the transmitted signal is simply reproduced with the help of regenerative repeater. It will not produce or introduce any extra that is additional information with the input signal. It simply reconstruct what is the information we have, simply repeat the information what we have transmitted to the next end, that is another device. Next device what we have available at the transmission path. Next we'll have the receiver end regenerator. First block is regenerator, then it will go to the decoder. So here the decoder, the digital pulses, the digital codes are converted into the respective samples. The digital codes are converted into respective samples, simply the opposite function of encoder. That sampled pulses are reconstructed as a waveform by using a low pass filter. By using the smoothing operation, we are getting a smooth wave as like our input message wave. So we are reconstructed our original signal back. This is the detailed explanation about pulse code modulation system. So, as I told earlier, we'll have the transmitter section. In that, we'll have four important blocks. The first thing is low pass filter, second one is sampler, third one is quantizer, fourth one is binary encoder. The first, we are transmitting our message signal x of t, or we are passing our message signal x of t to a low pass filter. In that low pass filter, our um, mm, the sampled signals are getting sampled by using a sampler. We are using natural sampler, so we are getting natural sampled signal at the output of the sampler circuit. Then it will go to the quantizer. What is the Q level quantizer is? The level of the quantizer is Q. Then it will go to the binary encoder. So we are getting the coded pulses, binary pulses at the output of binary encoder. Then this is the graphical representation of the inputs, graphical representation of the inputs and outputs of our transmitter section. The first waveform is our analog input, which is which is sampled by the sampler. We are sampling using natural sampling method. Then it will go to the quantization, and this quantization we are getting a discretized signal. This is regenerative repeater section. Simply we can say our transmitted pulses are reconstructed here. So this is the look at the diagram. This is the second waveform is the signal received at the starting point are received by the regenerative repeater. While traveling, due to the propagation, the transmitted pulses gets distorted like this. The first waveform is transmitted pulses, original input signal. Look at the diagram. This is the original input pulses that will be distorted like this. Okay, so we have to reconstruct that signal by using regenerative repeater. What are the blocks we have inside the regenerative repeater is, will have a amplifier combined with the equalizer, then regenerator, then timing circuit. What is the function of the amplifier combined with the equalizer? In the sense, amplifier is used to boost up or amplify the received pulses, and equalizer is used to minimize the ISI, intersymbol interference. It's a kind of noise that is added with our message signal during the propagation through the air. So the amplitude boosted signal and ISI free signal is transmitted over the regenerator. The another input of the regenerator is timing circuit. The function of timing circuit is it will produces the pulses with the sampling time. Okay, it will produces the uniform pulses at the sampling time interval. That pulses is multiplied with the reconstructed signal in the regenerator. So regenerator will produce the a reconstructed signal as like our original signal is transmitted. Then this is the pictorial representation. So the first thing is our original pulses. Then it will go to the at the starting point at the input. Simply we can say the input of the regenerative repeater is like this. The output of the regenerative repeater is like this. So the amplitude get boosted here. Now this is the receiver section of PCM. So as we know that PCM signal is added with the noise, then it will be go to the regenerator. So at the regenerator, we are getting the distortionless PCM signal that is going that is passed through a DAC, digital to analog converter. That DAC signal is get sampled by using a sampler. Then it will pass through a low pass filter. In that low pass filter, the cutoff frequency FC will be set as FM. So we are receiving or we are extracting only our message frequency alone. We are getting back our original message signal XFT. Then we are going for differential pulse code modulation. This is the advanced version of PCM, pulse code modulation. In that PCM, we are simply taking the present sample values. We are not bothering about the previous samples and past samples at all. Okay, but in this case of differential pulse code modulation, as the name implies, we can say we are going to take the difference between two successive samples. That difference is coded. That difference is represented with the coded pulses. That's why it is said to be the differential pulse code modulation. So we are going to take the difference between two successive samples. That difference is coded. Okay, that difference is coded with the uh, coded as the distal pulses. This is said to be differential pulse code modulation. We can say differential pulse code modulation is a signal encoder that uses the baseline of pulse code modulation but adds some functionalities based on the prediction of the samples of the signal. The input can be analog signal or a digital signal. The successive samples, I told the word successive samples. The successive samples may be the exact value of the signal or it may be the prediction of the next sample values. That is the thing they have mentioned. It is the prediction of samples. It is the prediction of the samples. Okay, so this is nothing but our message signal x of t is passed by the low pass filter, then sampler, q level quantizer, then we are getting a binary encoder sequence of binary pulses. Okay, so differential pulse code modulation transmitter. So look at the diagram carefully. We are going to get the prediction of the next samples here. The difference between the original sample and the predicted value is calculated. That difference is quantized and encoded, transmitted to the receiver. This is the concept. So we have the input signal here. The input signal sample value is simply said to be the x of NTS. That x of NTS is going for the summer. Okay, basically x dash of NTS. Just consider this is the prediction value of the previous sample. Simply first iteration we are consider it is 0. So we are going to calculate the difference between x of NTS and x cap of NTS. It is the prediction of x of NTS. Okay. Then it will be calculated. Simply the first iteration, the value will be 0. So we are going to take the first sample value as it is, and we are calculating the error value E of NTS by adding these two, or by finding the difference between these two. We are getting the error values E of NTS like this. That error value will go to the quantizer. The error value will go to the quantizer. Quantizer is used to quantize the at the output of the quantizer. We are getting EQ of NTS. We are getting EQ of NTS. That EQ of NTS will go to the encoder. So that EQ of NTS is encoded, excuse me, encoded and transmitted to the output. That EQ of NTS will go to the summer. The another input of the summer is X cap of NTS. These two signal is added and given as the input to a prediction filter, that is XQ of NTS. So prediction filter will give you the output X cap of NTS. So prediction error we can calculate it as E of NTS equal to X of NTS minus X cap of NTS. Quantizer output EQ of NTS equal to E of NTS plus Q of NTS. Prediction filter output is XQ of NTS equal to X cap of NTS plus EQ of NTS. Substitute EQ of NTS here. So we are getting XQ of NTS equal to X cap of NTS plus E of NTS plus Q of NTS. Rearranging prediction error, E of NTS plus X cap of NTS equal to X of NTS. XQ of NTS equal to X of NTS plus Q of NTS. Then differential pulse code modulation receiver will have a DPCM signal. That signal is decoded. With the help of decoder, we are getting a decoded pulses EQ of NTS. EQ of NTS. Then that EQ of NTS is added with X cap of NTS. So we are getting XQ of NTS. That XQ of NTS is passed through a low pass filter. From that we are getting our original signal XQ of NTS. The formula for xq of NTS equal to x cap of NTS plus EQ of NTS. This is the SNR of DPCM. Simply we can go through that. SNR of DPCM is sigma m square divided sigma q square. Sigma m is nothing but a message signal. Sigma q is quantized signal. Simply we can say SNR of DPCM is GP into SNR of Q. And GP is processing gain. The formula for processing gain is sigma m square divided sigma e square. So we can see the problems. Those problems and all we have already seen. Simply we refresh that problems. Which the first thing is, which one of the following statements about differential pulse code modulation, differential pulse code modulation DPCM is true? So what is the concept of DPCM? We are getting the simply refresh. We are uh, we are taking the prediction of samples. That samples that the prediction value and original sample value get sampled, get quantized and transmitted to the coded pulses. So they look at the first statement. Which one of the following statements about differential pulse code modulation is true? The sum of message signal sample with its prediction is quantized. Sum of message signal sample, okay, with its prediction is quantized. This is the first statement. Message signal and the prediction is quantized. Okay. The next statement B is the message signal sample directly quantized and its prediction is not used. So what is the conclusion? The option B, the input, they are taking only the input signal. They won't consider about the prediction, right? So this won't be a true, because what is the concept of our DPCM is message signal sample and prediction is taking into the account. So the statement B won't be true. The third statement, the difference of message signal sample and a random signal is quantized. No, we are not considering about the random signal and all. So that statement also won't come. The difference of message signal with its prediction is quantized. The difference of message signal with its prediction. Here we are using only the message signal prediction values. That is true, but we are going to take uh, we are going to take the difference. So the option D is we are going to take the difference between message signal and the prediction. So that will be true. So the first option A, they have mentioned sum of message signals, sum of these two components. That won't be true. So the option D will be the answer. Okay, option D will be the answer. Next, a sinusoidal message signal is converted to a PCM signal using a uniform quantizer. The required signal to quantization noise ratio, SQNR, signal to quantization noise ratio at the output of the quantizer is 40 dB. The minimum number of bits per sample needed to achieve the desired SQNR is 7 to 7. Okay, then the modulation scheme commonly used for transmission from GSM mobile terminal is, which modulation scheme we are using in the mobile transmission is the first option 4QM, second option 16 PSK, third option Wall Shada Mod orthogonal codes, fourth one is Gaussian minimum shift keying technique. This what is the answer is Gaussian minimum shift keying technique. GMSK technique, GMSK modulation and scheme commonly used for transmission from GSM mobile terminal. Those are all the diagrams we have already seen the last class itself. So from 12, from 12th problem we have to see. So what is the problem is a speech signal band limited to 4 kilohertz and peak voltage varying between 5 volt to minus 5 volt, plus 5 volt to minus 5 volt is sampled at the Nyquist rate. Each sample is quantized and represented by 8 bits. Okay. If the bits 0 and 1 are transmitted using bipolar pulses, the minimum bandwidth required for distortion free transmission is. So we have given the data band limited signal, that is our input message signal 4 kilohertz, that is varying the amplitude of the input message signal varying between 5 volt to plus 5 volt to minus 5 volt. Okay, then it has quantized with the help of quantized in the format 8 bits, and the bits is varies as 0 and 1. What is the minimum bandwidth required for the distortion free transmission is 32 kilohertz. By using the formula we can find out it is the 32 kilohertz. Next problem. A speech signal a speech signal band limited to 4 kilohertz and peak voltage varying between plus 5 volt and minus 5 volt is sampled at the Nyquist rate. Each sample is quantized and represented by 8 bits, assuming the signal to be uniformly distributed between its peak values. The signal to noise ratio at the quantizer output is 48 dB. I repeat the question again. A speech signal band limited to 4 kilohertz and a peak voltage varying between plus 5 volt and minus 5 volt is sampled at the Nyquist rate. Each sample is quantized and represented by 8 bits. Assuming the signal to be uniformly distributed between its peak values, the signal to noise ratio at the quantizer output is 48 dB. Next question. In delta modulation, the slope overload distortion can be reduced by. Before discussing the question, what is that distortion available in delta modulation is we have two kind of distortion: slope overload distortion and granular noise. So, what is the cause, or how can we reduce slope overload distortion? And what are the options we have? Decreasing the step size. The option A, decreasing the step size. Option B, decreasing the granular noise. Option C, decreasing the sampling rate. Option D, increasing the step size. So, the first option, decreasing the step size. If we decrease the step size, it will be reduces the granular noise. It won't be reduce the slope overload distortion. So the first option won't come. What will be the second option in the sense? Decreasing the granular noise. Granular noise is one of the disadvantage of delta modulation. So it won't come. The third one is decreasing the sampling rate. There is no relation between slope overload distortion and sampling rate here. So it won't come. So what will be the option D is if increasing the step size. If we increasing the step size, the slope overload distortion can be reduced. If we increase the step size, the slope overload distortion can be slope overload distortion can be reduced. Next, if the number of bits per sample in a PCM system is increased from n to n plus 1, the improvement in signal to quantization noise ratio will be. If the number of bits per sample in a PCM system is increased from n to n plus 1, the improvement in signal to quantization noise ratio will be. So what will be the improvement? What is the formula to find out the signal to quantization noise ratio will be S bar n. Signal to noise ratio is alpha plus 6n. This is the formula. Alpha plus 6n, that 6n will be considered as 6n plus 1, right? So 6 n is improved from n is improved as n plus 1. So 6 into n plus 1 can be written as 6n plus 6. 6n plus 6 dB. So the answer will be, the improvement in signal to quantization noise ratio will be, how long it will be increased as 6 times it will be increased. So the option B will be the answer. Option B will be the answer for the first problem. So what is the problem? If the number of bits per sample, if the number of bits per sample in a PCM system is increased from n to n plus 1, the improvement in signal to quantization noise ratio will be increased by 6 decibel. The formula is 6 times of n. So the n is increased as n plus 1. So 6 into n plus 1 will be the formula. So we are getting 6. So next problem is, the number of bits in a binary PCM system is increased from n to n plus 1. As a result, the signal to quantization noise ratio will improve by a factor. The number of bits in a binary PCM system is increased from n to n plus 1. As a result, the signal to quantization noise ratio will improve by a factor. Will improve by a factor. Option A, n plus 1, 1 divided n. Option B, 2 power of n plus 1 divided n. Option C, 2 power of 2 into n plus 1 divided n. Option D, which is independent of n. So what is the formula for a signal to quantization noise ratio is, another formula, S by n can be written as 3L square into C. Okay. L can be represented as 2 power of n, number of levels of the quantizer. L is nothing but number of level of the quantizer. So we can write the above equation as 3 into 2 power of 2n, 3 into 2 power of 2n into C. 3 into 2 power of 2n into C. Okay. Next, if we substitute into this equation, a signal to noise ratio equation, 3 into 2 power of n plus 1 into power of 2 into C. Like that, if we substitute, we will get 2 as the answer. So what is the conclusion is, which is independent of n. So we can say the number of bits in a binary PCM system is increased from n to n plus 1. As a result, the signal to quantization noise ratio will improve by a factor The option D is the answer, which is independent of n. The third question, the signal to quantization noise ratio in an n-bit PCM system. The SNR S by N quantization noise, signal to quantization noise ratio in an n-bit PCM system depends, option A, depends upon the sampling frequency employed, is independent of the value of n, increasing with the increasing value of n. Option C, increasing with the increasing value of n, decreases with the increasing value of n. Okay, the signal to quantization noise ratio in an n-bit PCM system. So the first thing is we have to write the formula of SNR, signal to quantization noise ratio, S by N equal to alpha plus 6n dB. Another formula for SNR is SNR equal to 3L square into M of T square divided MP of square. So simply we can say 3 into 2 power of 2n into C. So what is the conclusion is, if the value of n is increasing with n value, the signal to quantization noise ratio also increases. So the option 3 will be the answer. Next, the bandwidth required for the transmission of a PCM signal increases by a factor of what percentage, what the value, when the number of quantization levels increased from 4 to 64. So what is the question again? The bandwidth required for transmission of PCM signal increases by a factor of what, when the number of quantization level is increased from 4 to 64. Okay, so the number of quantization level they are mentioned as L. So what is the formula is bandwidth n into fs by 2, where fs is sampling frequency, then where n is number of quantization level caps L. So L can be written as 2 power of n. The value of n is initially 4, equal to 4 equal to 2 power of n. So the small n value will be 2. Look at here. The L value, capital L equal to 2 power of n. The value of L equal to 4. They are mentioned in the problem. The 4 equal to power of n. So the value of small n equal to 2. Okay. Then we know that the value is increased from 4 to 64. Number of level is increased from 4 to 64. So the value of small n value equal to 6. So we can say we can find out the bandwidth difference between the value of n is 2 and 6. So bandwidth equal to sigma n into fs by 2. This is the for the case. This is for the case n equal to 2. The first thing is maximum value. Bandwidth 64 divided bandwidth 4. So bandwidth 64 in the sense the small value is 6. So 6 into fs by 2 divided 2 into fs by 2. So Fs by 2, Fs by 2 is get cancelled. So we are getting 6 by 3. 6 by 3, we are, if we simplify that, we are getting 3 as the answer. So what is the answer is option A. The bandwidth required for the transmission of a PCM signal increases by a factor of 3 when the number of quantization level is increased from 4 to 64. Next, in a PCM system with uniform quantization, increasing the number of bits from 8 to 9 will reduce the quantization noise power by a factor of option A 9, option B 8, option C 4, option D 2. So I read the question once again. In a PCM system with uniform quantization, increasing the number of bits from 8 to 9 will reduce the quantization noise power by a factor of what? As we know that the formula for signal to noise ratio is S by N equal to 3 by 2 into L square. So what is the formula for L? 2 power of 2N, right? So the value of N is increased from 8 to 9. The number of bits, increasing the number of bits from 8 to 9. So how can we say that? So look at here, we are having the formula S by N equal to 3 into L square divided 2. L is the quantization level. It will be represented as 3 by 2 into 2 power of 2n. N is number of bits increased or used. Here, the n value is varies from 8 to 9. So simply we can say 3 by 2 into 2 power of 2 into 8, 2 into 9 divided 3 by 2 into 2 power of 2 into 8. So we are getting 2 power of 18 divided 2 power of 16. So the if we simplify this, we are getting the value as 4. So the option C is the answer. So we can say in a PCM system with the uniform quantization, increasing the number of bits from 8 to 9 will reduce the quantization noise power by a factor of 4. Next, next problem is compression in PCM refers to relative compression of higher signal amplitudes or lower signal amplitudes or lower signal frequencies or higher signal frequencies. So compression in PCM refers to relative compression of, so look at the diagram, we'll have a signal like this noise signal. So noise get increases if the amplitude of the signal gets increases. Okay, it won't get if the frequency of the signal increases like that. It doesn't depend upon the frequencies, it only depends on the amplitudes, right? So simply we can say compression in PCM refers to relative compression of higher signal amplitudes. Relative compression of higher signal amplitudes, it will not depends on lower signal amplitudes and lower signal frequencies and higher signal frequencies. Then next question, choose the correct one from among the alternatives A, B, C, D. After matching an item from group 1 with the most appropriate item in group 2. So we are having matched the following like that. So look at the group 1, we have FM, DM, FM frequency modulation, DM delta modulation, and third one is PSK, phase shift keying, fourth one is pulse code modulation. In group 2, we have slope overload option as we have the first option is P, slope overload. Second option is Q, Mula. Third one is R, envelope deductor. Fourth one is S, capture effect. Fifth one is T, Hilbert transform. Sixth one is matched filter, like that. Okay. So what are the things it will be related with that? We'll look at the explanation. So the first one, FM is related with matched filter. Sorry, FM is related with the capture effect. Okay, DMS. What is the drawback of? Look at the slide. Yeah. So what is the word regarding FM, frequency modulation? The sense slope overload. It's related to the delta modulation, and Mula is related to the compression. Third one is envelope detector. It's related to the AM. Fourth one is capture effect. It is related to the FM. Fifth one is Hilbert transform. Sixth one is matched filter. So for the FM, the appropriate answer is capture effect. Next one is delta modulation, DM. What is the relative word DM we have is the first option P, that is slope overload distortion. One of the distortion available in delta modulation. Next, we'll have the PSK, phase shift keying. What are the word regarding PSK, Mula? The options available are Mula, Q option Q, then option R, envelope detector, then T, Hilbert transform, and the fourth one is matched filter. Fourth one is matched filter. So what will be the appropriate answer for PSK is matched filter. Okay. The fourth one, that is pulse code modulation. Here we'll have the compression technique, right? So that is Mula compression technique. So look at the option A, B, C, D. The answer will have third one is the exact one. The correct answer is third one. So what is the third one abbreviation? FM is related with capture effect, and second one delta modulation related with slope overload. Third one PSK is related with PSK is related with matched filter. PCM is related with Mula compression technique. Next question. In a PCM system, if the code word length is increased in a PCM system, if the code word length is increased from 6 to 8 bits, the signal to quantization noise ratio improves by the factor 8 by 6, 12, 60, or 8. So what is the thing? We know that we have the formula S by N equal to 3 by 2 into L square. Code word length length is increased from 6 to 8. So how can you write the value of small n is the value of L, the capital L. So the value of capital L is 2 power of value of capital L is 2 power of n. So we have L square here, 2 power of 2n. The value of n is increased from 6 to 8. So substitute in this equation. The highest value will be in numerator. So if you substitute 3 by 2 into 2 into 2 power of 2 cross 8 divided 3 by 2 into 2 power of 2 cross 6. So we have 2 power of 16 divided 2 power of 12 equal to 2 power of 4. We can say it is 16. So the answer will be option C, 16. In a PCM system, if the code word length is increased from 6 to 8 bits, the signal to quantization noise ratio improves by the factor 16. Next question. A speech signal is sampled at 8 kilohertz and encoded into PCM format using 8 bits per sample. The PCM data is transmitted through a baseband channel via 4-level PAM. The minimum bandwidth in kilohertz required for transmission is. So, what are the data they are given? A speech signal is sampled at 8 kilohertz message signal frequency and encoded into PCM format using 8 bit per sample. The value of n, small n is 8 bits. The PCM data is transmitted through a baseband channel via 4-level QAM. So, the quantization level Q value is 4. The minimum bandwidth in kilohertz required for transmission is what? Okay, so we know that the value of m quantization level, all caps L or caps M, we can represent in both variable equal to 4. The sampling frequency f is equal to 8 kilohertz. Mm, and small value n equal to small n value equal to 8 bits. So um, here we'll have n into fs, the bandwidth, the minimum bandwidth required for transmission as n into fs, 8 into 8, 8 into 8, that is 64 kilobits per second data rate. If minimum bandwidth is um, n into, that is s into bandwidth divided 2 power of sampling bandwidth divided 2 into log of m with base 2. So the value of bandwidth is 64 kilobits per seconds divided 2 into log of m, caps m, that is 4, equal to 64 divided 64 divided 4 equal to 16 kilobits per seconds. A signal is sampled. Next problem. A signal is sampled at 8 kilohertz and is quantized using 8-bit uniform quantizer. A signal is sampled at 8 kilohertz and is quantized using 8-bit uniform quantizer. Assuming SNR for a sinusoidal signal, the correct statement for PCM signal with a bit rate of RS. So we have to assume SNR of a sinusoidal signal. Okay. So what are the data they have given? Look at the option they have given R equal to the first option they are given R value and SNR value. Okay. So first thing we have to write the equation for R, that is R equal to N into Fs. N is number of bits used. So the value of N equal to 8. Sampling frequency sampled at the rate F is equal to 8 kilohertz. So the capital R equal to 64 kbps. Okay. Then what is the equation for SNR? SNR equation is alpha plus 6n, right? The value of SNR is alpha plus 6n. So alpha value, we have to, it is a default one. We have to know that clearly the value of alpha equal to 1.8 plus 6 into n. Okay, so 1.8 plus 6 into the small value of n equal to 8. So what will be the answer for this problem is 42.8 dB. Sorry, 49.8 dB. So the answer will be option B, that is capital R equal to 64 kbps and SNR value equal to 49.8 dB. 49.8 dB. Okay. Next problem. Um, um, a discrete memoryless shows as an alphabet A1, A2, A3, and A4 with the corresponding probabilities. 1 by 2, comma, 1 by 4, comma, 1 by 8, comma, 1 by 8. The minimum required average code word length in bits to represent this source for error-free reconstruction is the minimum required average code word length in bits to represent the source for error-free reconstruction is they have mentioned average code word length. They are asking average code word length. Okay. So we have to find out the entropy first. H of x equal to summation of I is varies from 1 to 4. Pi log of Pi log 1 by Pi. Pi log of base to 1 by Pi. So what are the probabilities we have? We have four probabilities. That is 1 by 2, comma 1 by 4, and 1 by 8, and 1 by 8. So substitute here. So 1 by 2 log of base 2 into 1 by log of base 2 into 2. Similarly, we'll have like this. So log of base 2, we have to find out the log of 2 value and divide that with 0.3010. And then we'll have, if we simplify that, we'll get 1.75 bits per seconds. Okay. So that is the average code word length. Average code word length. Next problem. An analog baseband signal band limited. An analog baseband signal band limited to 100 hertz is sampled at the Nyquist rate. The samples are quantized into four message symbols that occur independently with the probabilities P1 equal to P4 equal to 0.125 and P2 equal to P3. The information rate bits per seconds of the message sources. So the information rate caps R, we have to find out the R. How can we find out? By using the formula R equal to R into H of X. So as usual, we have to find out H of X. How can you find out the entropy value H of X in the sense? By using the formula that is Pi log of base to 1 by Pi. Using that formula, we can find out the value of H of X. The value of H of X is 1.811 bits per seconds. And we have to find out the value of small r. Fm equal to 1 megahertz. So the value of sampling frequency equal to 2 into 100, that is 200 hertz. So the Fs value is 200. That is, the small r value is 200. Is multiplied with entropy h of x 1.811. So the value is 36 to um, the value is 362.2. That is the information rate of the message source. Information rate of the message source. So what is the conclusion is, one of the important topic in regarding the gate, especially in distal modulation topic is PCM, DPCM, and delta modulation. Those are all the important topics we have to concentrate on more. We have to concentrate on more. In that, especially, we have to concentrate on the formula, that is signal to noise ratio of the PCM. S bar n equal to 3 by 2 into L square. This is the one of the important formula we have to remember in our mind. The value of L is 2 power of 2 power of n, 2 power of small n. The value of n is number of bits. That is the thing we should keep it in our mind. So so we can conclude that, wind up with PCM and DPCM problems. Thank you all. Thank you for participating in this video.